Okay, so in the last part, we looked at a few theoretical examples. Here we see a more practical example of coupling between the heat pump system and the building. This is a system that delivers heating and cooling at the same time to the building. We have a plate heat exchanger on the right and a plate heat exchanger on the left for the cooling, on the right for the heating, with two buffer tanks, one tank for the heating and one tank for the cooling. Again, we have a separation between the building circuit and the heat pump central because we want to prevent antifreeze mix going through the building. Therefore, we have heat exchange over two plate heat exchangers. The heat pumps in this case can provide cooling to the building on the evaporator side and heating to the building on the condenser side. The heat delivered to the building is regulated by a 3-port valve to the plate heat exchanger, where any warm water generated by the heat pump that is not being used is put into the buffer tank. The return is from the plate heat exchanger also goes into the buffer tank, so the buffer tank is used for decoupling of the flow rate over the plate heat exchanger and the heat pump, and at the same time it is used as a store if we have sufficient temperature difference, sufficient hysterese on the set points. For instance, if we want to deliver 45 degrees to the building, we can have the buffer tank going between, let's say, 48 or 50 degrees and 45 degrees, still delivering 45 degrees to the building, but having storage in the tank as well. The ground source, the boreholes, are coupled to the system based on the maximum energy required at a certain moment. In the graph we see here, we had delivered 21 kilowatts on the cooling load and 32 kilowatts on the heating side. This means that we are delivering more heat than cool, and the cold side of the system will be coupled to the ground to, let's say, replenish the heat that we cannot extract from the building at this moment. In summer, therefore, the hot side, the condenser side, is coupled to the ground, whereas in winter, the cold side, the evaporator side, is coupled to the ground. But the ground only delivers the part that cannot be extracted or rejected to the building itself. That was a closed loop system. Here we look at the same type of layout for an open loop system with two groundwater wells. Then, of course, the ground side is slightly more complicated with a plate heat exchanger in between to separate the groundwater circuit from the building or heat pump circuit. And as there is water now on the heat pump side, we do not need a plate heat exchanger between the building on the cold or the hot side anymore. We have a direct connection on the building side, but the plate heat exchanger between the groundwater wells and the system. One thing to note here is that we switch over the wells between winter and summer operation. Then the flow direction will change. On the building side, this is not the case, so we will need a method, in this case by 4 motorized valves to, let's say, change the flow direction in the plate heat exchanger on the building side as well. And another thing that we can see here is a dry air cooler, again integrated with the plate heat exchanger, because on the dry air cooler we do have antifreeze to prevent freezing in winter. The dry air cooler is used to either, let's say, balance the heat load on the ground, cool load on the ground, but also it can be used to directly reject condenser heat during peak load cooling. Some optimization strategies are possible. For instance, an optimization by temperature compensation, where we say, okay, if the ambient temperature is below a certain point, in this case 12 degrees C, we need a high flow temperature to the heating system, 47 degrees C. But if the ambient temperature is high, in this case 15 degrees C, we can do the heating with 38 degrees. In between the 12 and 15, then we interpolate the flow temperature set point to the system. Of course, the lower the flow temperature on the heating side, the higher the efficiency. Another method of optimization is to take a good look at the pump control. Here on the right, we can see a curve of the energy that the pump uses in part load conditions. So if we keep the temperature difference on the ground source side the same. We can throttle back the pump in part load, and we can see that instead of 1.8 kilowatts at 100% of the duty, at 20% of the duty, we only use 0.7 kilowatts. So a very big gain in efficiency on the ground source pump. We can calculate the percentage of the time that the pump will run in different part load conditions and use this to estimate the SPF. In this case, we can see that the performance with the pump on fixed speed, so always running at 100%, will be around 3.9. But if we make the pump variable speed, the efficiency increases to about 4.42. So a significant improvement of the efficiency of the system. Another important factor, especially with regard to the lifespan of the compressors, is the number of on-off cycles on the compressor. Also, the efficiency is affected by this, but of course the failure of the compressor, the failure rate of the compressors is of very big importance as well. Here, what we can see on the left, the blue lines are the start-stops of the compressor. So we have a high frequency of starting and stopping of the compressor. And the orange line, the buffer tank temperature, we can see that we maintain a very close control around the required set point of around 6 degrees. Now, this was not really a good way to operate the system. So we increased the hysterese on the buffer tank. We increased, let's say, the difference between the lowest and the highest temperature that we allow, so that the heat pump comes online when we reach the highest temperature, let's say 16 degrees, and then it goes off again when we reach the set point or slightly lower, around 5 degrees, and we can see that it did not really improve the start-stops on the compressor itself. However, if we did this and also increase the set point from 6 degrees to around 10 degrees, we can see a huge improvement of the start-stops on the compressor, and also the behavior of the whole system in a thermally way is much better in this case.